So today we will talk about this very it's like a common sense 常识课 常识. You think plate tectonics or plate structure for people in Taiwan is like what you learn as at your kindergarten maybe. But what I mentioned during the Q&A session is actually there's something that's very different from what you learn during your school, especially regarding the upwelling limb of a convection cell, of a mantle convection cell. And I hope after this class you will remember this, and because this is actually it will change your idea regarding the plate tectonics. Usually, you can imagine there's general issue like what's your perception, your understanding of plate boundaries. Then you will say, there's a divergent zone, convergent zone, or you say there's lateral fault, St. Andrews 就是合一断层，圣安德鲁断层，或是聚合带、张裂带。That's what you learned during your school, and what's your perception? And what's your perception of the mechanism of platonics? Then 100 out of 100 students in Taiwan will draw this and say, okay, that means mantle convection. So our school education is really successful. Okay. Plate boundaries. Okay, so during school, you will just learn here. The plate boundary here, but actually as a geoscientist you will start to learn other plate boundaries. For example, this one is quite famous because we know this is Europe, and Italy is the heart of European culture, more modern civilization. So this is a subduction zone, and also for people who study PhD in the United States, they will study the plates here. It's quite complicated. But here, we know that it's subduction. It generally subduction here. Okay. And here, this map has some more information. So this means change. Change means subduction or collision. Collision means there's no subduction. Or that also means mountain building. So here we learn that African plate we have ridge, but we have subduction here. And around Taiwan we have subduction. We have a lot of subduction. No, sorry. Some of them might be mountain building. No, these are all subduction. Okay, right. That's what you have in mind. But today we will say there is some problem here, and during our first hour we already point out what is the problem. And during the next hour, I will tell you more about the evidence. Alright, so to talk about plate tectonics, we first start with Earth's topography. Then here comes the phrase again. So I said, the more a mountain is eroded, the higher it is. And why is that? Because its root moved up. So, and that is because of isostasy, like a eureka, so it's Archimedes' principle. Floating plates on the asthenosphere must displace a mass of liquid equal to their weight following this principle. So we have seen the three models in the previous hour. And as mentioned, this one applies to different continental crust. And this one applies to continental crust to oceanic crust. But overall, this is the model. You might ask, what is the evidence? And the first evidence has been, we have talked about it, which is the post-glacial rebound. This is something that can be measured and has been measured. And the other, more direct evidence comes at gravity anomalies. So this is actually geophysical evidence. So maybe some of you might have heard 重力异常. You might think, what is gravity anomaly? So this is a principle. This is Mantle, and there is a block of continental crust. Let's assume that this block corresponds to mountain. If mountain has roots, 有根的话, it should look like this. And if the mountain does not have root, and if the mantle is not ductile, 不是塑性的, that would be like two blocks piling up, 就是像两个积木堆在一起. This is mountain, this is mantle. Then the model, the theory, or the model will be like this. So there are two models. And which one better explain mountain? You can imagine, of course you have to imagine, there is an observer who is observing or measuring the gravity at the horizontal line, which would be the a reference point. And in this case, or in this case, the reference point should be at the same level. Then you can imagine that the observer who measures gravity, because we know gravity is related to the mass. Then the observer standing here will measure less gravity than the observer here, right? Because here the density is all 3.3, but the observer standing here will measure the block first with a density of 2.6 and then 3.3. So this case will have lower gravity. And we have an equation here, but it's not important. So what you need to know is, in these two models, the observer will detect different density, or different gravity, sorry. So, and indeed, that is what was found for mountains. For example, in Taiwan's case, you will see mountains always have negative gravity anomalies. So gravity anomaly is another way to prove that mantle is ductile. Otherwise, you should not measure negative anomaly for mountain. And why mountains have negative anomaly is because of the concepts here. Okay. So, therefore, mountain have roots, and because mountain have roots, so mantle is ductile. So, this is a logical link. And this is another piece of evidence, and then the first piece of evidence is the post-glacial rebound, and we have discussed this. So I will not talk too much about this here. Okay, so now we know mantle is ductile, but does it convect? That's another level of question, because a material can be ductile but not convect. For example, your jam, your 你的果酱 is ductile, but it does not convect in your jam, in your can, right? So we know from our previous slides that many evidence supports confirm that mantle is ductile and may flow. But what is the mode of movement? Then no one can observe the whole mantle. That's the reason why scientists have to use computer modeling. and the Rayleigh number. And all the parameters here can be measured. So you don't need to measure the whole mantle. And you can have a rough picture how the flow, mantle flow may look like. And Anna has introduced the equation here, so I will skip. And the viscosity of mantle is really high. It is 10 to the 24th time greater than the viscosity of water, which is 1. And as mentioned before, when the Rayleigh number is higher than 2000, convection is inevitable. And the model results show that the Rayleigh number of mantle is extremely high. And as Anna has mentioned, this is because of the term delta T, the temperature difference, and the distance. The mantle has a long distance and large temperature gradient. That's the key controller of convection. So this model is based on Rayleigh number of 10 to the 5th, and this one is to 10 to the 7th. And the actual condition is between these two. So, the conclusion from scientists is, yes, mantle convex. Yes, mantle convex, but can mantle flow explain plate tectonics? That's the key topic today. So we are not just concerned about mantle convection, but plate tectonics. Okay, so in Bella's talk, we talk about African plate. So it's extremely strange. Consider that there's a plate which has it has 4 margins, but 3 of the 4 margins is divergent zone. So in theory, the plate should become smaller, right? But this is apparently not the case. The plate is not shrinking. And actually, there are many other strange relationships between mantle, convection cell, and plate boundaries. So no simple correlation, as mentioned in Bella's talk. I don't remember which one. And here is a very strange case. In this strange case, there's a phrase called final nail in the coffin. What does that mean? That means 就是有点像压死骆驼的最后一根稻草。So this is the ultimate evidence that killed the classical theory of plate tectonics that you learn in school. So here, this is Vancouver. So this is Oregon, California, and this part is called the Cascadia margin. It's also a conversion. It's a subduction zone. Okay. However, this plate is called Huanda-Fuka plate, and at the left side of the Huanda-Fuka plate, we have the ocean ridge, and to the north, we see that this ridge is subductive. So, if a convection cell truly corresponds to, if this one is the downwelling and this one is upwelling, then can upwelling and downwelling take place in one spot, like here? Can you imagine that? So it's really difficult to explain this with this classical convection cell concept. So that's the reason why we said this is the final nail in the coffin. And that's the reason why this place is quite famous, because of this strange tectonic configuration. So a ridge is subductive. It's really weird. There's further evidence, but I will skip this one. So, the key concepts of today's topic is for what you learn in high school, the ocean ridge, Yangji, it's passive upwelling, which means in what you learn in high school, the teacher told you, because of upwelling, the plate is ruptured, pushed open apart, and then the magma can flow out, and the plate spread apart. That is so-called active upwelling， 就是主动涌升先涌升，再撕开再裂开这叫主动涌升However, this is wrong. It is not the active mantle convection that results in spreading. No. Instead, it is the spreading of crust that induce mantle upwelling from shallow depths. In other words, the crust spread first, and because it spread and there is a gap there, and because mantle is ductile, so the fluid, the magma has to flow in to fill the gap, and because it's upward movement, the magma can melt. That's what we mean, passive upwelling. So repeat again, crust spread first, and then magma mantle move upward, and because mantle move upward, magma forms because of pressure release melting. So this is what we believe. What explains the ocean ridge. And the magma chamber is relatively shallow, maybe only 100 kilometers. Okay, so of the upwelling, the ocean ridge is not what you learn from high school. But subduction, how about it? Subduction cannot be a shallow process. This is confirmed by seismic studies. So maybe from some news, you will see a graph like this. So this is distance. I think this one corresponds to the AB line. And this is the depth from seafloor. And these are the depths of epicenter, 正央. And based on the exact positioning of epicenter, scientists figure out that epicenter tends to cluster along a belt or a zone. And this zone is named Benioff zone. Apparently this is the name of the scientist, Benioff zone. And you see based on its shape, that will remind you the shape of a slab, right? A subduction plate. So this is considered a good evidence of a subduction slab, and it can penetrate really, really deep into mantle. Like here, it's up to 250 kilometers. And distribution of, so this is distribution of epicenter or earthquakes. That is actually down to 700 kilometers. And there is more evidence. So here there's a technique called seismic tomography. So tomography is in medical studies like CT 断层核磁共振断层扫描. Its English is tomography, computer tomography, CT. And here it's like you do a CT for the Earth. So that's the reason why it's called tomography. So this is a CT of the Earth. And here, this is a CT of Central America. I think this is East and this is West. So, and CMB means core mantle boundary. We are not that familiar with Central America, so let's look at Japan. CMB again. So east and west. So this one corresponds to this one, right? And you see, the change is here, and you see a black zone here. You might ask, what's that? So generally, all seismic data determine the seismic speed. And seismic speed is related to the property of the material there. So usually we have high speed or low speed zone. And usually if a material is brittle, 就是脆的, or hard, that material will have higher speed. And if a material is ductile, that material will have low speed. And if a material is pure liquid, like our outer core, then you will not see any speed for the S wave, right? So here you see different color. That's actually the seismic speed. And this one is the high speed zone. So because of this data, scientists think this is correct. You see, based on the seismic topography, the high-speed zone is all the way down to the core mantle boundary. And even at the core mantle boundary, you can see something lying here, right? So this is right. So plate can descend to the core mantle boundary. So what causes plate to move? It is now generally accepted that plates glide over mantle rather than riding along with mantle convection cell. So it's gliding, 就是滑行的. It's gliding over mantle. And upwell magma come from shallow depths where, so 100 kilometer in ocean ridge, whereas subductive slab may descend down to the core mantle boundary. But what causes plate to move? Then this comes to one of the assignments. This mechanism, now if you Google plate, if you use Wikipedia and search some web page regarding plate tectonics, you will see the term ridge push slab pull. And it is now believed to be the mechanism. Alright, why plate move? So the mechanism is like this. Here, when the ridge is formed, it's a high land in the ocean. 就是海底的高地. So elevated ocean ridge, it will create a potential energy, 位能. So it will push the plate away in a manner of a gravity slide. It's like a high mountain, and because of its high elevation, not because of the mantle upwelling, but because of its high elevation, it will create a potential energy. And this potential energy will create pressure to the material next to it. So it's called ridge push. And as when the oceanic seafloor it reaches a subduction zone, we have hydrated basalt because we know oceanic crust is made of basalt, and the density is 3.0. However, this one is anyway heavier than the continental crust, which has a density of 2.65. So it will go beneath the continental crust, and then when it goes beneath the crust, it will be compressed, and the pressure will result in higher density. So in other words, it's metamorphosis, 就是变质作用. Then the basalt will form amphibolite. And then, with even higher density, it will form eclogite, which has a density of 3.6. So mineral undergoes phase change to high density material along, subduction. The denser material acts as a dragging force. So it's like during this subduction, we have a plummet here， 就是你有一个铅锤挂在这里，这个铅锤还会随着这个加压越来越重，密度越来越大，所以它就一直往下拉。然后那一头就是遥远那一头的那个阳极那边是有位能的驱动，那边不是永生的驱动，那边是位能造成的驱动。然后这边是密度变大造成的驱动。In this way, this plummet is dragging the slab downward, and this is now believed to be the mechanism of plate movement. Okay, and the more within slab pool is more important than ridge push. This process here. So subduction is an important driving force of plate movement. All right. So I think you should have learned this during your first year of university. Mantle plume is also called hotspot. It's also called intraplate volcanism because most hotspots take place inside the plate. It's not at the plate boundary. It's inside the plate. Okay. Read. While 90% of Earth's current volcanism is associated with plate boundaries, a significant number of volcanoes occur in the middle of plates. This is quite important. Examples: Hawaii, Yellowstone, and many, many others. We can later take a look on the global map. There are many, many mantle plumes. The magma of hotspots has a deep origin. Remember what I said? Subduction can reach a deep depth, down to core mantle boundary. And the magma of hotspot also has a deep origin. This will will match better with the feature of subduction zone. Both should have a deep penetration. Evidence: geochemical, geophysical, geomorphological. Okay, so I think you should all have learned about the case of Hawaii. Here we will use the chance to introduce this dating technique, the potassium-argon dating technique. This is the most commonly used dating technique to date volcanic rock. So we know potassium is present in volcanic rock, especially, it's in volcanic rock. And this one can decay to argon. This one is solid, but argon is a gas. And this isotope pair has a half-life of 1.25 to times 10 to the 9 years. So it's quite long. Skip this. So how this works? In Taiwan, it's possible to do this kind of dating. So what you should do is, for example, if you have volcanic ash in marine cores, in theory, you can also do this. So this one is very useful. In molten rock, so when a rock is in magma, so let's do this again. In magma, there is potassium. And when magma upwell to surface, it might be in the beginning in molten state, so melt. And in molten state, argon can escape to the atmosphere. However, when a magma reaches the surface and when the temperature cools down, the magma will start to recrystallize. And when the magma starts to recrystallize, argon as a gas will be trapped in the lattice, 晶格, 矿物的晶格, will be trapped in the lattice of minerals and start to accumulate. So this tells you in the lattice of minerals, it's possible to host gas molecules. Okay, and therefore the potassium argon H represent the most recent volcanic activity because it represents the last time this material is molten and recrystallized. And argon-40 can be measured by dissolving the rock under vacuum, which means you have this material, you put this into a vacuum system and evacuate remove all the gas, and then you melt the rock with HF. So you know a rock can be melted with hydrofluoric acid, then you can measure, you can collect the argon for measurement. That's potassium argon dating. And then this is the dating technique used to measure this famous Hawaiian ridge. And in the Pacific, actually there are many other chains of islands, all in this direction. And here, this is the age. This is the distance from Hawaii. We know Hawaii has volcanic activity today. And 0 means Hawaii. And it has the youngest age. And the further the island or the seamount is away from Hawaii, the older it is. I think you have learned this many times. Hank, what does that mean?
Because this part is where the youngest magma come out and it spread to the far place, and this will be the oldest volcanic rock.
Do you mean the magma here? I think this one corresponds to this one, roughly, right? The magma or the volcanic rock you find here, it's spread, it comes from here. Is that what you mean? Yes? Like the ocean currents, 海流, move the volcanic rock from here to here. Is that what you mean? Sounds weird, right? Do you have other explanations? Pinjun, how do you think?
I think the plate
You talk to the microphone.
the plate
Northwest.
northwest. So this point is originally here.
Very good. So this point was here. And the source that created magma has not moved at all. The source has been sitting here all the time. What has been moving is not current, but the plate. So the plate moved from here to here. So this is the first magma produced by the source here, and the source has a name, hotspot or mantle plume, this case. And the set applies this one. And you will see that because all the seamount has this orientation, this is a good proof that they are all formed by the same mechanism, which means a hotspot here, a hotspot there, and there again. And the plate move roughly all in the same direction, but you see there's a turning point.
So if we see the three hotspot arc, then we will see the three same slope.
Same slope?
Yeah, the slope about this diagram.
Yeah. In theory, you should. In theory, you should. But what does the slope mean? What do you think?
The plane move, 移动速度.
Okay, exactly. The moving speed of the Pacific plate. That means we have more evidence. So this is geochemical evidence. Now we have geophysical evidence. Again, we resort to seismic tomography again. But now this time we look for something with low speed. Remember? High speed corresponds to something hard and brittle. Low speed corresponds to something ductile. So here, seismic shows magma chamber below Pacific Islands. On the map at the end, at the back side of the classroom, you will see that all the seamounts is barely visible. It's barely visible in the ocean. It looks like they are unimportant feature on Earth. However, if you do seismic tomography, you will see that each of them is like a little bit like iceberg again. The small tip corresponds to large mantle plume. So these are all low velocities. We call these fingers. 有点像手指啊，低速指啊，震波的低速指。These below these seamounts, they are always gigantic, 巨大的 low velocity seismic fingers beneath them. Therefore, I think these are very good evidence that they are mantle plume. Direct evidence. I will skip this one. This is again seismic tomography studies, but I prefer this one. I prefer this one. This one is a little bit like 3D reconstruction, and this one is the raw data. The raw data will be a little bit 就像你们 CT 扫描，一开始都是一张一张一张，然后再拼起来。这个也是原本一张一张。But they talk about the same story. And some mantle plume extend to the core mantle boundary. So again, it's a deeply rooted feature. All right, I think I will skip this one, too complicated. So, what we know about the location of mantle plume today is like this. A lot. And in fact, if you look at the backside of the global map, you will always see some strange seamount in the middle of plate. For example, we have a lot of seamount, chains of seamounts here, and you will see in the Indian plate we have this strange seamount here. It does not correspond to any plate boundaries. And also at the west side of the African plate, you see this strange seamount. It's actually extend all the way to the continents. These are all large mantle plume that we know today. And I think this one is not even complete because We don't have the seamounts here. But these are the known, some of the known mantle plume, location of the mantle plume. So the upwell magma in mantle plume balance the mass introduced by subducted slag. That's the consensus, 就是共识, the consensus of geoscientific community today. So now I will introduce this new model of plate tectonics and mantle convection. We have inner core and outer core. And this is a thin crust at the surface of the earth. And here we have a thick mantle. What we know previously about oceanic ridge, you should view it as a small rupture on the skin. 就是阳极，它是有点像你皮肤上面的小破皮。It's a very thin, small rupture. And the real big structure in plate tectonics, the first one is subduction, like this one. This is subduction, this is subduction. And based on seismic tomography, we know that the subducted plates, they tend to rest at the outer core. 它们会躺在那个外核那边，就躺在那里。But in fact, scientists already know that below the African crust and the Pacific crust, there is two large graveyards of plates, 就是两大板块坟场。This one is African large low. Is that right? Right. African large low shear velocity province and Pacific large low shear velocity province. The reason why they are low shear velocity because the plates here already start to melt. These are dead plates, and they lie there and they start to melt. Okay, and regarding the upwelling part of convection, that is mantle plume. Mantle plume here. Okay, and there are other features that but I will not introduce it. So that's it's actually not new. I think it's established in 1990s already, but we are apparently not updated. So, new model regarding plate tectonics. This is another view. So, subduction and mantle plume. And ridge is only shallow, small rupture at the surface. Next week, we will talk about hydrothermalism, 就是热液电子。First question, A group. How does water and carbonate affect the geochemistry of the subduction zone? Water, carbonate. So read this and explain this. So table 12-2 is this table. Please explain this. Figure 12-7 and -9. This is figure 12-7. This is the reaction that geochemical reaction that takes place at the subduction zone. And water plays a crucial role. So explain this effect of water. A group. B group. For B group, in the textbook there's no related text, so you have to search internet material. What is serpentinization? Where to find it? So answer the questions. What are the minerals involved? What are the gases produced? And why is it related to the origin of life? There's a theory saying that this is related to the origin of life. So answer these questions.